Hi, this is Dan Detmeyer with Amphenol Broadband Solutions. Welcome to our Fiber 101 training series. In this series, we're covering the basics of fiber. We're going to break this down into several different sessions. In this session, we're going to be covering fiber cable and connectors. During this training, we're going to be taking questions. At the end, we'll address those questions. So feel free in the chat or the question area to put your questions, and at the end, we'll address those. The glass optical fiber is made up of three components: the core, cladding, and the coating. Here I'm showing the single mode fiber, where the core is 8 to 10 microns in diameter. The core is the central region of the optical fiber where the light is guided. In order to create the guiding conditions, the refraction index of the core must be higher than the one of the cladding. The cladding is the region of the fiber surrounding the core. In order to create guiding conditions for the light, the refraction index of the cladding must be lower than that of the core. With the cladding and the single mode fiber, it's normally 125 microns. The coating is the non-glass layer of the optical fiber, and basically what this does is some mechanical protection of the glass. The coating absorbs the shocks, nicks, and scrapes, and the moisture that could damage the cladding. You wouldn't think that water would have an impact on the cladding, but with that, water can be absorbed into the glass. The coating is typically made up of two layers of acrylate. The first coating is a soft layer, and this is applied right over the cladding. The second layer is a harder coating, and this provides protection against nicks and damage. Fiber optic cable has very high tensile strength. With the fiber optic glass, it actually has a higher tensile strength than steel of the same diameter. Like a plate glass pane, if it's scored or bent, it can break pretty easy, usually along the score line. So when you're handling fiber optic cables, be very careful that you don't nick the fiber optic glass. Since the fiber optic is made of glass, it can be very fragile when bent too far, and it will break. So again, just be very careful how far you actually bend this. Fiber optic cables need to protect the internal fibers and provide access and fiber identification for routing and end termination. Here I'm showing a couple of pictures on the top. On the left, we need to protect this fiber optic cable from any kind of damage from like backhoes or construction. We also have to have easy access into the fibers, and that's where the ripcords come into play. Since there could be a lot of fibers in a bundle, they need to be color-coded so it's easy to identify which fiber goes where. On the bottom, fiber optic cables need to provide strength against the tensile loads that can come from construction. This could be aerial construction where they're lashing on the strand or pulling the fiber through conduit. Also, we need to protect it against storms, high winds, and then we have our furry friends, the squirrels, that can actually chew the fiber and damage it. There's a couple different packages for the fiber optics. First, we'll look at the loose buffer tube. With the loose buffer tube, the individual fiber strands or fiber ribbon cables are loose within a buffer tube. Here I'm showing the different components. We have a blue buffer tube, and we can have up to 12 fibers per tube. Within that tube, there's a water repellent. It could be a gel or dry. This is used to prevent moisture from going down the fiber cable. Then there's going to be some sort of a protective yarn, an armored yarn, very similar to Kevlar, very strong. And then we're going to have some sort of protection as an outer jacket. This is to protect it from mechanical damage. With these fiber bundles, there can be a lot of fibers within one bundle. And that's where they came up with a color code for the buffer tubes themselves and the individual fibers. Over on the left, you see the different colors. There's 12 fiber colors. There's blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, and aqua. And we have the same color code for the buffer tubes themselves. So when you look at the combination between individual fiber colors and the buffer tube colors, now you can get up to 144 fibers identified in one bundle. There's a lot of times when you need more fiber. And what they do there is now they identify the buffer tubes with actually stripes. It could be black, orange, green. So this way you can actually get a large amount of fiber out into the network and still be able to identify which fiber goes where. Now, I can't stress enough that it's very important for documentation. So when you're actually looking at these fibers, you need to know where it's connected in the head end or the hub, to the last connected device. There's nothing worse than connecting a fiber you think goes one direction and it's not connected to anything. The fibers within the buffer tubes is loose and slightly longer than the tubes. This allows the fiber to move within the buffer tube when temperature variations cause the tubes to expand and contract. We can get very high fiber counts possible by utilizing multiple buffer tubes. So within this package here, we have multiple buffer tubes with up to 12 fibers per tube. Now, since the fiber is glass, we need to have some sort of strength member. So as we're using this for construction, hanging it in the air, pulling it through conduit, there's some sort of a strength member there. Also, there's a rip cord. This is easy access to the fibers. So by ripping that back, you can expose all the different tubes. Now, there is going to be an armored yarn again to protect it, and also the outer jacket. There's different packages for different needs out there. So if need be, we can actually add additional buffer tubes, remove that central strength member, and actually put the strength members out into the jacket themselves. Now, one thing with fiber optic cable, since it is glass, it's hard to locate it because there's no metal to actually locate the fiber. So these strength members can be made out of metal so you can actually identify where it is in the ground. Now with this, there is the armored yarn again, the jacket, but we can also package this with an armor. This will help protect against shovels and also the little critters out there, the squirrels and so forth, that can actually chew into the cable. And then we're going to have an outer jacket. So there's a lot of different packages that you can have out there. Contact your manufacturers for your specific needs. Then the second type of fiber out there is the tight buffer. Tight buffer fiber cables have armored yarn wrapped around the fiber to protect for strength. These are usually used for patch panel cables and so forth. So with the picture above, you're seeing the jacket and seeing the yarn wrapped around individual strands. You can actually have multiple tight fibers in one bundle. And here I'm showing multiple fibers wrapped around the armored yarn and then with an outer jacket. The best example of tight buffer is cordage cables. These are used to connect equipment and patch panels. They're color coded. So when you see yellow, that means it's for single mode fiber. When you see orange, that indicates that it's for multi-mode. So this would be for data centers and so forth. Multiple loose buffer tube cables are commonly used as the breakout cables where individual buffer tubes are accessed in the splice enclosures to drop fibers to OTNs and nodes. Here I'm just showing some pictures of what a splice enclosure would be in an underground location. And as you access that, it exposes the splice trays where these individual buffer tubes and their fibers into a splice enclosure. Now with today's technology and everything going fiber, we need more and more fibers out there. Ribbon cable is a solution for space and weight problems. We can get a lot of fiber out into the system with ribbon cables. The cable contains ribbon fiber, which are coated optical fibers placed side by side, encapsulated in mylar tape. You could have 4 to 12 fibers in a ribbon. These ribbons are encased in mylar, they're covered in armored yarn, and they have an outer jacket. To get more fiber out there, we can actually put these ribbon cables in loose tubes. The ribbon fibers are stacked on top of one another inside the buffer tubes. Here I'm showing multiple fibers in multiple buffer tubes. Drop cables are located on the subscriber end. These are needed for the fiber to the home applications, and they connect the terminal of the distribution cable to a subscriber's premise. They're typically small diameter and low fiber counts. The flat drop cable is the most popular one, where here's a single fiber with 2 support members in a flat cable. But there's a lot of different packages. With this, we can actually have a tight buffer tube. So this would be the single fiber wrapped in yarn and then an outer jacket. In this example, this is a tight buffer drop cable. We have 1 individual fiber wrapped around armored yarn with the outer jacket. We also have loose buffer tube drop cables. Within the loose buffer tube could be 1 or multiple fibers. Then there's also the hybrid solution. So maybe today you're not using fiber optics, but in the future you might. So today you'd be using the coaxial drop cable, but in the future when you need fiber, it's there for you. Then here's the same type of solution, but in a loose buffer tube. And there's also hybrid cables that have no fibers in them. So the buffer tube is empty. So maybe you don't know how many fibers you need in the future. So you use the coaxial cable today, and then when you do need fiber, you have a tube where you can actually pull the fibers through. The most popular drop cable is actually the flat. So you got the center fiber, 2 support members, and an outer jacket. Here's an end view of this. It's actually made up of a UV resistant jacket. It has dielectric support members. Attached to it is a tonable copper element. Again, since it is glass, we actually need something that we can actually tone and locate with. So that's why that element's there. And then within there, we have a jacket, and then we have our armored yarn, and then we have the optical fiber itself. And this is just what it would look like broken out. With the flat drop cable, or any drop cable, it can come in predetermined lengths. So it might be 25 feet, 50 feet, 75 feet, 100 feet. This can be used to pull through conduit. So on the drop cable itself, there's actually a pull loop to pull it through the conduit, and then it'll have a hardened connector on it. So next we'll get into connectors. And with the connectors, the purpose of them is very similar to why we use connectors with the coaxial cable. We need a way to connect or terminate to different devices out there. The connectors are going to provide a mechanical, environmental protection, and also importantly, it's going to minimize reflections that can happen out there. Factory manufactured patch cords and pigtails control the reflectance of connectors by machine polishing the fiber end face during the manufacturing process. So let's look at the different connector ends. The first one is the flat. With the flat connector, this has a minus 30 dB back reflection. What this means is that not all the light escapes out the end of the fiber. Some of it reflects back and is lost. Some of you old timers out there probably remember using figure 8s to polish the ends of these fibers. But we've come a long way from that. The next type of connector is the PC, or the physical contact. This has a minus 35 dB back reflection. So if you notice, it's actually rounded, which exposes more of the core and the cladding. So when they mate together, there's less loss and less reflection. The next type of connector, this is the UPC connector, or the ultra physical contact. This has a back reflection of minus 55 dB. And if you notice, it's actually more rounded than the PC. So the more of the core and the cladding are exposed to each other. And then the last one, which is probably the most popular connector out there, is the APC. It's the angled physical contact, which has a minus 65 dB back reflection. So if you notice, it's angled, but also it's a little bit rounded. So this has the best mating and has the best back reflection. There's different types of optical connectors out there. One of the more popular ones is the subscriber connector, or the SC connector. Then we also have a smaller connector. It's called the lucent connector, or the LC. And then there's a phase contact, or ferrule connector. This one's not seen as much in the cable industry. There might still be some out there in the hubs. With the SC connector, again, this is the most common type of connector you'll see out there. It actually has a 2.5 millimeter ferrule. It has a push-pull coupling mechanism. and also a key, so it only goes in one way. So it also has a strain relief boot, and what this boot does, it just prevents it from having too tight of a bend as it exits the equipment. As we talked earlier in the first session, we don't want to have too much attenuation. So the SC is the most common type you'll see, but they're color-coded as well. So the green, when you see green, that means that it's an SC with an APC connector in it. When you see the blue, that means it's an SCPC connector or a UPC connector. Now with the color codes, you can't intermix them. So it has to be green to green or blue to blue. If you try to intermix them, you're going to have way too much loss and issues. One thing you got to be careful of is that if you're putting these connectors in or out, that you don't pull an adjacent connector out or damage the connectors themselves. There's actually tools you can utilize to pull them in and out. The next type of popular connector is the LC. It's a small form factor connector. So as we're getting more and more fiber out there, we needed to reduce space in our head ends and our hubs. So by doing so, we actually reduce the size of this to 1.25 millimeter ferrule. It still has the clip latch mechanism and a key, has a strain relief boot, and it's half the size to get into the SC. Now we can increase the density by 100% versus utilizing the SC connectors. So it's all about saving space out there anymore. So more and more fibers are being needed. Now these optical connectors need to be connected to adapters. So these adapters could be on the back side of devices. In this case, we're looking at muxes. It could also be in enclosures on the side of a house. Again, green to green. So don't intermix green and blue. Now, a couple other types of connectors that are becoming popular is the MDC connectors. With these connectors, we can increase the capacity by 3 times compared to the LC connectors. So you can fit 3 fibers in a space where you would have the 2 of the LC connectors. So we're actually utilizing this space more efficiently. And then with this, there's also the CS connectors. Again, reducing space, 39% reduction compared to the LC duplex connectors. So here we're looking at the fiber to the home type application connector. And we call this the hardened connector, the H on the right. So inside of this connector is a subscriber connector, the SC APC. With fiber to the home applications, we talked about pre-connectorized jumpers, but in this application here, this is where you'd actually run the exact amount of fiber that you need, and then you would actually put the connector on in the field. There's a lot of different manufacturers out there, so as you're doing this process, just make sure that you follow the manufacturer's instructions. The H connectors for the fiber to the home applications, they're designed to withstand the rugged outdoor plant environments, and they're environmentally sealed. Here I'm showing the flat drop cable again with the H connector installed. Now with these H connectors, they're going to mate with a fiber to the home optical tap. So these optical taps could be aerial or they could be underground. There's also mini multi-port terminals. The large optical taps take up a lot of space. To solve that issue, there's a mini multi-port terminal that can fit in small enclosure spaces. So with connectors, it's very important to make sure that the connectors stay clean. Here I'm just showing the back of a patch panels and the equipment that was seen in the head end. With this, you'll see that some of the connectors don't have protective caps on them. So they're not used fibers, but the protective cap should always be on them. So anytime that you're going to be using a fiber, you keep the cap on until you're ready to install it. Here's an outdoor enclosure. You can see all the dirt and debris down there. So it's very key to make sure that these optical connectors stay clean and protected. Here I'm showing a view of the end of the fiber optic cable. So this would be using a fiber optic scope to look at it. This is a clean connector. When you talk about the core, that's 8 to 10 microns in diameter. So when you start looking at dirt and dust, just a little bit, on the optical core itself can reduce the attenuation of the fiber. Here's some dirt and it looks like a little bit of grease. It might be from a hand and so forth. But anything, again, that's blocking that optical core, That can be an issue. That can cause attenuation and problems. Here's an optical connector that was exposed to water. Water actually damaged this fiber optic cable. And again, some more dirt. You can see right over the core, a big speck of dirt. And here's some more with maybe grease or so forth. So this could be from your hands. I just want to stress that out in the field, probably 90% plus of the issues is due to dirty connectors. So you always want to make sure that these connectors stay clean. Now with the connectors, I talked about end caps, so you want protective caps on the fibers. Anytime you're using this fiber, if it's not being used, make sure that there's a protective cap on it. When you look at the adapters on the end of the equipment or the back of the equipment, make sure that the plugs are there. So with connectors, there's several ways you can actually clean these connectors. So always follow your manufacturer's recommendation or your company's policy. Thanks for attending this Fiber 101 training session on cables and connectors. I know we had several questions that came in during this session, and I'm going to take a quick break, go over to my laptop, and check to see what those questions are. In the meantime, if you have any additional questions, please put them in the chat and we'll address those. All right, let's look at the chat questions that came in here. We have several. The first one's from Kate, and it asks, is the cladding also glass? And the answer is yes, it is. It has a lower index of refraction than the core. And we covered this in the first session that we did about a month ago. And this should be available on our website. So if you want to reference that session as well. So hopefully that answers your question. You can also type any kind of additional questions in the chat there, and I'll keep an eye out for that. So the next question that came from Charles. It says, is it necessary to bond or ground fiber optic drops at the subscriber's home? And with this, the National Electrical Safety Code basically says that with the fiber optic cables, which is non-conductive, but any metal part of that, which might be the tonable element that goes into the customer's home, would have to be bonded or grounded. Most of the times you have an enclosure on the side of the house where you transition to another type of fiber cable going to the house that has no metal element in it, so you would not have to bond there. But my best response here is, the National Electrical Safety Code says one thing, but always check with your company policy, because they're in connection with the local authorities and they know what the proper procedures are. So hopefully that answered your question there, Charles. Looks like Marion has a question. What is the typical loss of a fiber connector? And the typical loss of the mechanical fiber connector is 3 dB per connector. Hopefully that answers your question there, Marion. And then we have one from Gerald. Is it necessary to attach the fiber drop cap to the tap dust cap during installation? And that question answer is yes. With the H connectors there, you don't want to just leave those caps open because they can get moisture or dust in them. And later on, if you ever had to change that, disconnect it and put those caps back on, you don't want to get dirt and debris inside those connectors. So the answer is put them together and keep that dirt and debris out. So hopefully that answered your question there, Gerald. I don't see any others. We can wait just a few seconds here. You can still type those in. And we do appreciate you attending this training. Amphenol Broadband Solutions is going to, we're doing this in a series. So the next session is going to be covering the transmitters, the receivers, other optical devices out there. So be sure to keep an eye out for the invitation for that. That'll probably be sometime in mid-January. So we're looking forward to doing that one. So after the holidays, and I don't see that we have any more questions come in. So enjoy the holidays, and we'll see you in mid-January with part 3 of transmitters, receivers, and other optical devices. So thanks for attending. Bye now.